Redis Enterprise is the database for the instant experience that powers any data model, any deployment option, and a multitude of use cases. See why more than 7,100 customers worldwide, including Microsoft, Staples, and Twitch, choose Redis Enterprise for their database needs. Visit redislabs.com/InfoQ.
Hello and welcome to the InfoQ podcast. My name is Wes Rice and I'm the co-host of the podcast. The InfoQ podcast is a weekly show from the people who organize InfoQ and QCon, a lot of times with speakers and interesting folks doing things with software. Today on the show, we're talking to Louise Poubel. Louise is a software engineer at Open Robotics. At Open Robotics, she's working on free and open source software for robotics, like the robot simulator Gazebo and the robot operating system ROS. Louise first got involved with Open Robotics through the GNOME Outreach Program for Women. Louise grew up in Brazil, went to college in Japan, and received her BS in electrical mechanical engineering from Chuba University. Her research has been focused around real-time whole-body human motion imitation by humanoid robots. Today on the podcast, we're going to talk a bit about robotics. We're going to talk about what that means for software engineers. We're going to talk about simulation. We're going to talk about developer experience when it comes to building these systems, and we're going to have a lot of fun. So, Louise, welcome to the InfoQ podcast.
Hi, Wes. Thank you for having me here.
So last time I heard you talk, I think was at San Francisco QCon a year ago. I think that's what it was. You introduced us to Dolly. Dolly, I'll let you explain who she is, but has Dolly done any more shows, presentations, or anything?
Yeah, Dolly has been following people around for a while. I talked about Dolly at UCSC in Santa Cruz some months back, and I also am planning to take Dolly to Japan in September, and Dolly might make it to Macau in October. We'll see.
Nice.
Dolly is all over the place.
I guess we should let people in on who Dolly is.
So Dolly is a robotic sheep. Like a sheep, it follows people, and like a dolly, it carries heavy stuff. And like Dolly the sheep, it can be cloned, and because it's open source. So it's not really a real physical robot. I'm not trying to sell Dolly or anything like that. It's just a simple example that I developed using some common robotics tools as kind of like a hello world example for people to get their feet wet with robotics. So it's just a virtual robot that lives inside a simulator. It's not a physical robot. It's not going to actually move and follow people around in the physical yet.
The two reasons that I wanted to do this podcast with you was one, to talk about robotics because, well, it's cool. And I wanted to talk a bit about the idea, the process, what it looks like with building an application that runs the robotic operating system and how you test that out. But the other piece was that virtual bit, that simulation bit that you just talked about. First off, simulation is one of the first places that a more traditional web stack software engineer who moves into like robotics might touch. So I think that's interesting. And I also find it super interesting because in software, we talk about canaries, we talk about, our CI/CD pipeline, we talk about testing and production, we talk about a lot of these concepts that in the real world, when you're moving things around that can actually collide with people, we can't just, test that way. So I'm just curious to talk more about simulation and see what we can learn and just kind of explore where things go from there.
Sounds good.
So first off, let's talk about Dolly, building Dolly. When you talk about building that, you talk about sensing, you talk about actuation, you talk about logic. Let's talk about those things. When you build a robot, what are the things you need to focus on?
Yeah, so robots, the high-level view of our robot application consists of mainly like the sense, think, act cycle, how it's called, which is basically the robot. First, it acts. We're not talking about a robot that just lives inside a computer, kind of like a chatbot or something like this. It's robots that are physical when they are going to act on their environment. They're going to move themselves or they're going to move other objects, right? So they need to act. They need to have actuators. They have motors. And then they're not just moving blindly. They're just not like a wind-up toy that you just like, turn it on and it goes. It's actually like taking information about the world and making decisions about how it's going to move. So the way that it collects this information is through sensors like cameras, LiDARs, GPS, any way that the robot can collect information from the world. And connecting these two parts is the think, right? The logic. What is the robot actually trying to do? So when I designed Dolly, I tried to make these three parts very clear in the code and in the way that the code is organized to really like show how these three parts are working together in this sense, think, act cycle.
So when you talk about kind of sense, think, act cycle, is there like an event loop that's cycling through so that as this event loop is going through, there's a stage where I think I sense and then I act? Is that how that works?
That's pretty much how it works. So you can think of it as a loop that continuously works. So first the robot senses something. So in the case of Dolly, Dolly is using a planar LiDAR to sense what's the closest point in front of it. And then once it gets that information, it passes to the think, right? Actually, the sensing part is only getting the LiDAR data, right? And then when it goes to think, the logic of the program is the part that is saying, okay, Dolly is going to follow. So I have to find the first point that is in front of it. So that's the thinking part based on those LiDAR scans. And then once it finds that point, it says, well, Dolly has to move in a certain way because I know Dolly's current position. So Dolly has to move in a certain way to go face and go move there. And then it sends that command to the act, where the act is the one that knows the robot's kinematics, knows how the robot can move its motors to perform that movement, right? Because Dolly happens to have wheels, but Dolly could have legs. And the thinking part doesn't care about whether the robot has wheels or legs. It just cares, where should the robot go? And that side of it is the one that actually knows the kinematics of the robot, knows the dynamics, how the robot should move, and moves it. And once it moves it, the robot actually moves in the world, then that sensor data changes, right? Because now the robot is in a different relative position with respect to the goal. And then we start the loop again, because then the sensing picked up something new, and then it reasons again what's the closest point and acts again. So you keep on this loop.
Is that like a time-based loop that happens over so many intervals? Is there some notion of a cycle? How is that based?
So since we're using ROS, and ROS is not a centralized application, it works as a distributed application. So there is not anything taking it. It's different from the simulator, for example, and we can talk about it. But the simulator has a ticking, like you have each step that goes through the cycle. But for the actual robotics application, it's just everything's there, just waiting for events to come and trigger them. So in the case of Dolly, what triggers an event is when it receives new sensor data. So the moment that the sensor, the LiDAR, generates some sensor data, that goes to the think loop, to the think node, which is like the part of the program that is doing the reasoning, and it triggers that chain, right? So basically, Dolly's system happens to run at the rate of the sensor. When you have a complex application that will have multiple sensors, each one with a different update rate, you might want to have a better way of coordinating that.
So something else you just said kind of triggered me. So it's an event driven from the sensor. So there's events, the immutable stream of things that actually happen are flowing through it. And then you observe, kind of watching for these events to be able to respond to them?
Yeah, that's basically it. It's just responding to these events. So the LiDAR is configured to a certain update rate, and inside its own node, it's running its loop and collecting that data periodically, right? And that happens in this system to be the main driver for the whole cycle to be spinning.
Yeah, so it's an event-driven system. Interesting. Okay. So you talked about the robotic operating system. What is ROS?
ROS is several things, depends on who you ask, but you can think of it as an SDK for robotics. So it offers a communication layer between all the different parts of your robot. So you can imagine there is a lot of data flowing around from sensors, and you have to send commands to actuators, and you have different parts of logic that are doing different things and they need to communicate. And ROS offers this common communication layer, like it acts as a middleware in between all these different parts of the robot and make sure that they are all speaking the same language and using the same tools.
So is that event stream that we're talking about? That's that message bus that's flowing through the middle, and then each part is like responding to those events on the bus?
Exactly. So in Dolly, the three parts that are running in Dolly, there are three ROS nodes, we call them, which are units of logic. So it's one for the sensor, one for the actuation, and one for the thinking, the logic. And the messages between them are ROS messages. And they're going through ROS topics. So ROS uses a publisher-subscriber type of communication. It's one of the communications in ROS. So the main one is pub-sub, but there are others as well. In the case of Dolly, it only uses pub-sub, and that's how that information is flowing. From the laser, it's just publishing. The laser scans for whoever wants to hear. And the think node wants to hear, so it's receiving that data. This is the core of ROS. It's basically this communication layer.
I should have asked before, is this all C? What are each of these nodes programmed in?
So ROS is multi-language. So there's ROS 1 and ROS 2, and we can talk about them and their differences. But ROS 1 is mainly implemented in C++ and Python. So it has these two versions, and these are the versions that I believe most people use, but it has also been implemented in a variety of other languages. And as long as they agree about the data that is flying in the wire, you can use your nodes and you can implement your nodes in any language that you want. So there's JavaScript, Rust, Java, there's, you name it. If there's a language that people are using for robots, they're going to be a ROS library for it. For ROS 2, which is a little bit different, the core is actually implemented in C. And on top of that, there is a thin layer that you can do in a different language. So we at Open Robotics, we're maintaining the C++ and Python layers. So they're thin wrappers on top of that C common layer. And there are people in the community implementing Java, Rust, other languages. But we are not the maintainers of that. And the idea is that this common C layer is reused between all of them, because in ROS 1, the whole stack was custom. And in ROS 2, there's that common C layer.
So I think last time when we talked, ROS 2 wasn't quite released. It was in active development, and I think Dolly was built based on ROS 2. Is ROS 2 released? What's the status of ROS today?
Yeah, Dolly uses ROS 2, and ROS 2 is actually on its fourth named release already. So we've been doing named releases since December 2017. And like ROS 1, we used to have named releases every 6 months, and then the cadence became longer and longer as the code base became more stable. But ROS 2, we're still doing the 6 months releases, and we released dashing in May 2019, and it's the first LTS. So it will be supported for 2 years from the previous ones that were only supported for a year. And this is the first time that we're telling people like, you should actually look into ROS 2 if you're starting a new application now and you don't have any ROS 1 code yet, and you want the advantages that ROS 2 brings with respect to ROS 1, you should really look into using ROS dashing, because that has a lot of the core features that people expect from ROS, and it has a lot of the integrations. It has the simulation integration, it has the navigation stack, it has a lot of the things that people expect when they use ROS 1 are already there.
I guess it's also worth noting, I think you said in your talk that was at QCon SF, I think you talked about that ROS has been around for, at that point, like 12 years. So it's been around.
Yeah, ROS has been around for 12 years, since 2007, ROS 1. And the development of ROS 2 started 5 years ago in 2014. So ROS 1 stack is pretty old, right? In software, 12 years is very long. So it was about time to do some refactoring, using some newer libraries, building on top of other things that are out there, like DDS, right, which ROS 2 builds on top of. So the whole communication layer is not custom like ROS 1 had a custom communication layer. So everything is updated now.
What is DDS?
DDS is Data Distribution Service. It's a standard for PubSub, for publisher subscriber. It's maintained by the OMG consortium. I think it's a consortium. And it's already used and proven in a lot of mission critical use cases. So like nuclear power plants and airplanes, they've been using DDS for a long time. So now ROS 2 builds on top of DDS and adds all the ROS specific concepts and tooling on top of it.
So I want to go into bootstrapping an application and specifically talk about what you need and how you test, like with simulator, and talk a bit about that and kind of that whole process. Before we do that, you've talked about Open Robotics a couple of times. What is Open Robotics all about?
Open Robotics, we're a company in California that develops open source software for robots. And our two main products are ROS and Gazebo, as well as ROS 2, which is ROS's latest version, and Ignition, which is Gazebo's latest version. So we have a subsidiary in Singapore now, and we have some people working also all over the US. So we are almost at 40 people right now.
One thing about it, you say 40 people, but the system ROS is used in a lot of different places, right? Are there any you can talk about?
Oh, yeah. So like ROS itself started a long time ago, over a decade ago, and it didn't start with us. Its main growth started at Willow Garage, and ever since it's being used by thousands of developers all around the world. And this includes academia, but it also includes industry. There are robots being shipped out there running ROS today. And, if you're in a robotics course in a university, you're most likely learning ROS one way or another.
Are there any specific clients that you know of that are building?
Some companies that are using ROS now in production are, for example, there's Fetch Robotics. They're using ROS in warehouses, warehouse robots. There's also ClearPath Robotics. They made ground robots that can be used outdoor or indoor. There are like some self-driving car companies that are using ROS. NASA is running ROS in their robots in the International Space Station.
Oh, wow.
Yeah.
Cool. So it's nice. You can say you put some of your software into space. Nice. I want to talk about now, what does it actually take to take that logic and put it onto a physical system? And in particular, I kind of want to go through that space about simulation and talk a bit about how you can iterate fast and quickly to test things out with it. So what does it look like to go from ideation to a physical robot? What does that kind of process look like for you?
There are people using simulation for prototyping their robots before they become a physical robot. So you would start like just like in the real world, you would need parts to build your robot, and you would need to think about their physical properties, like how much it does it weigh, where does it connect to what.
So is this something like with a CAD program you design and build, and it gives you kind of like your bill of lading? This is what you need, what it weighs. Is that abstracted into ROS? So it's like physical components that I design and build. What does that look like?
There is a couple of description formats. One of them is SDF, the simulation description format, and another one is URDF, the Universal Robot Description Format. Both of them are supported by Gazebo to simulate your robot. So you start with describing your robot in these terms, right? So they're both XML based. So you will have an XML tag saying, this is the friction of this part, and this is how big it is, and this is how bouncy it is, and this is the joint that connects to this one, and this is how the joint behaves. Does it have a spring? Does it rotate infinitely? Does it slide? So you would describe your robot in these terms. So it's kind of like a CAD program. You can import parts that you made in a CAD program. You can even import the parts that you make in a CAD program for your physical robot that you're going to use in production to manufacture it. And you can take that same one and use inside your ROS ecosystem with Gazebo and with other tools.
Okay, so you build this physical description of what a robot looks. You have to instrument this event stream and observe to kind of like sensors that are publishing information, move the robot with actuation and logic that decides on how all this stuff operates. Once you kind of get that first iteration, do you do like small little releases into CAD, or not CAD, to simulation to see it move? What does that process look like, that deployment process before you put it on a robot?
So you can start with something very simple, just like with boxes and cylinders, kind of like Dolly. Dolly is just made up of boxes and cylinders connected by joints. And you just put it in simulation and start sending commands to it and seeing how it's behaving. And that's kind of like how you iterate on your algorithm, right? You write a little bit and you send the command to it in simulation, and you see if the robot is doing what you would expect. And this is very similar to how you would also test in a physical robot. In a physical robot, you would also kind of like have the robot there physically sitting next to you, and you would try sending different commands from your workstation to the robot to see how the robot behaves, right? So what simulation gives you is that robot is inside your computer, and you can more easily reset it. You can more easily see exactly what it's doing. You don't need to follow it around. There's no risk of the robot like turning around and hurting you. There's no risk of the robot just flying very far away and then you have to run after it and go pick it up. So you start with that, with the putting your robot inside the simulation, a very basic version of it, and you start working on your algorithms. And then it depends on what's your final goal. If you're still designing the mechanical part of the robot, you may want to iterate on the physical properties, right? You would write this XML file with some properties of your robot, and then change the properties a little bit and start simulation again and see how the robot behaves with a slightly bigger wheel or a slightly smaller wheel, right? And you can iterate on that, or you can iterate on the algorithm itself. So as you're sending commands, you would change the command a little bit. You would change in Dolly, would change the follow logic to say, oh, like I want you to stop if the robot is very close to the follow point because I don't want it to hit the person in front of it. And then you can play with that distance and see in simulation if the robot stops in time or not. So you can iterate on the logic, you iterate on the mechanics, and you can iterate on the environment around it, right? You can say, well, either through the UI of the simulator or through code, you can say, well, what if the person was here? How would the robot behave?
The first question that comes to mind is how accurate is the simulator? I mean, the simulator only knows what I tell it with the physical properties of the robot. So how realistic is the experience of developing against the simulator versus what the real world's going to see me?
That's a very good question. And that's something that I think, especially like software engineers may not be aware of when they start developing for robots, is that the real world is very chaotic. It's full of complex effects that you can't really simulate well and you can't really expect, right? It's a lot of unexpected things going on. So one example I like to give is you have a robot with two wheels and you just want it to go straight, right? So you would give the same speed to both wheels and you would expect the robot to go straight. In simulation, that's very easy because everything is very perfect. But if you try this in a real robot, what you're going to find out is that after a while, if the robot is going 100 meters, most likely the robot is not going to have gone in a straight line. It probably drifted a little bit to one side because the wheels are not perfectly the same size, right? It's impossible to manufacture wheels that are super perfect, or because there was a little rock on the way, or because the friction of the floor was slightly different in part of the path that the robot was following.
So basically, the wheels aren't perfect. You can't manufacture an exact same copy of it. So the question is, how do you build in that uncertainty into a simulator, a piece of software that you don't know what it's going to be raining outside or the wheels are going to be different size? How do you build all that uncertainty into it?
Exactly. And that's where you have to be creative when you create your simulations, and you have to vary your parameters a lot if you want your algorithms that you're developing to really be robust to various use cases. So for example, if you want your algorithm, and once it goes to the real robot, to really be robust to all this variation that happens in the real world, you have to test that in simulation. So you have to make sure that your simulation is not perfect every single time. And you have to, for example, if you're training a machine learning algorithm and you're running 1,000 simulations to train it, don't train it with the perfect robot every single time. Vary a little bit the position of the center of mass of the robot, or vary a little bit the sizes of the wheels, just to make sure that whatever solution you come up with is robust enough to withstand this kind of variation. And also, taking feedback from sensors is a great way of overcoming this uncertainty, right?
So one of the things you said as we were talking before is a lot of people love to use ROS. They truly like that experience. So what is it about the developer experience about ROS that makes people really want to use it?
I think that ROS just gives you that boilerplate that people who are really developing robotics applications don't want to have to deal with. So there is a lot involved into setting up drivers, setting up the tooling around to be able to capture the data from your robot and introspect what's happening in your system. And ROS gives you all of that for free. So I think that the flagship product inside ROS is Arvis, which is the robot visualization tool. And what it basically gives you is one single point for you to visualize all of the data that is flowing in your system. It doesn't matter if you have one robot, multiple robots, it's all going to be visualized within that one 3D scene. So that's very powerful because you suddenly have a way to put together what your camera is seeing and what your LiDAR is seeing, and where your robot odometry is telling the robot where it is in the world and where the robot thinks that objects are in the world. You suddenly have access to all of this in one unified view, and it's really easy to debug things when you have this kind of tooling. Another powerful tool in ROS is the command line tools. You can very easily just say, oh, give me all the nodes that are running right now and tell me which topics each node is publishing, and each topic, what is the rate? Has it been missing deadlines? Has it been publishing at the rate you would expect? So you can do all this introspection with the command line tools.
So your background, your formal training is a mechanical engineer, but you're a software engineer because you've been building this simulation software that runs this stuff for so long now. What are some things that the world of robotics you think can teach software engineering?
I think that there is this point of the uncertainty is an important thing that software engineers don't usually have to deal with, right? You're used to using an API, you make an API call, and you know exactly what you're going to get from that under those circumstances. And when you come to a robot, like I was saying, you tell the robot to go straight, and it's not guaranteed that the robot is going to go straight because you're interacting with the real world. So embracing this kind of uncertainty is definitely something that software engineers are not used to. And when they go into robotics, I feel like a lot of software engineers are comfortable with simulation because simulation tends to be perfect and you know what to expect from it, right? So you're in that friendly, familiar environment. While when you go to the physical space, it's a lot changing.
So expect uncertainty. Things are going to fail, expect a network partition, expect things to go down, just kind of embracing that kind of idea with your systems.
Yeah.
So what's next for ROS and Gazebo? What's on the roadmap?
So Open Robotics has been focusing on ROS 2 for the past 4 years. And in the last years, we've been like really focusing mainly on ROS 2, and ROS 1 is going to have its last named release in the coming months, which is going to be called Noetic. And after that, we are not going to be doing any more ROS 1 releases. So that one is going to be an LTS. It's going to be maintained for 5 years, like every ROS 1 LTS. And that's it. And we are turning all our focus to ROS 2, all our build farm, all of our infrastructure to ROS 2. So the next release is going to be Eloquent, also coming up in the next month before the end of the year, 2019. And the idea is to make ROS 2 as feature rich as ROS 1 is right now. For the simulation side, we're also not developing gazebos as people know Gazebo today, which is, we're calling it Gazebo Classic. And we are turning our focus to Ignition, which is the next version of the simulator, which is also much like the ROS 1 to ROS 2 transition. We are transitioning from Gazebo to Ignition to allow more flexibility for people to support more use cases. One of the important use cases really focusing on is running simulations on the cloud. So you can run them distributed across multiple machines. In this way, you can really run like huge simulations in huge environments, right, that you couldn't run in one computer. We're also improving the abstraction layer, so it's much easier for you to plug in a different custom physics engine into Gazebo or a custom rendering engine into Gazebo. We're also making improvements to the way models are hosted. So now we have an online model database, and it has a website and it has a REST API. So the simulator will take those resources from this online database, and you don't need to ship them with your application every time.
When you say model, you mean like a rendering, a physical model, not like a machine learning model.
Yeah,
right?
It's a robot model. So those SDF and URDF files.
If I got this prototype idea that I want to build, I can go out, download ROS, I can build some models, add some logic, add some sensing, add some movement, be able to encapsulate all of that and test it in Gazebo, all using open source tools from Open Robotics.
Yeah, and if you check out Dolly's source code, which is open, I made it in a way that it is really meant to be a Hello World program. So it has instructions on how to get set up, all using Ubuntu, because that's what the platform that I usually use. But ROS 2 is supported on Mac, Windows, and Linux. And Gazebo is recently also moving to be supported across all platforms. But anyways, you can use the Dolly example as your entry point, or you can use, like, we have a lot of tutorials online. You can check ros.org or ros2.org to see how you could get started. But it's all open source, and you just have to install it in your computer and start using it.
Very cool. Thank you, Louise, for chatting with us on the InfoQ podcast.
Yeah, thank you. It was great being here.